This Robin Hood problem is quite challenging, so take your time and make sure you understand all your steps. The goal of the problem is to figure out if Robin Hood was to swing down like a pendulum, grab the bag of money, let go of the rope, and land in the water, how far from his original location would he travel? So there's a lot of steps we want to go through to figure this out. So start out by drawing the system and put all of your information into your picture. So the first thing we know is that the rope has a length of 10.51 meters. Robin Hood, who will be mass 1, has a mass of 68.3 kilograms. The bag of money he's going to grab is mass 2, and that has a mass of 16.4 kilograms. It tells us the angle that the rope is pulled back from the vertical, so that should go in here. And it tells us how high he's going to be above the water when he lets go of the rope, and that is going to be 5.49 meters. Finally, it tells us that we're not on Earth and that we have a gravitational field a little larger than the Earth. So make sure you keep that in mind. Once you have all of these elements in your picture, we can forget about the question and start solving the problem. The first thing you want to do is figure out how high above his release point is Robin Hood to start with. So the way we're going to do that is to do a triangle, and we'll do the length of the rope in the X and the length of the rope in the Y. And to do that, we're going to use sine and cosine. So we're going to use cosine to get the Ly, and we're going to use sine to get the Lx, and obviously we'd use our hypotenuse to get both of those. So we'll have Lx, some number of meters, Ly, some number of meters. Check to make sure that they are logical. That is, once you get your Lx and your Ly, try using Pythagorean theorem and make sure you get back to the length of the rope. Also make sure that the Lx, in this case, is bigger than the Ly because I have an angle bigger than 45 degrees. If your angle is smaller than 45 degrees, then the Ly should be the bigger of the two numbers. Okay, the next thing we're going to do, and let me change up my colors here, is we need to find out how far Robin Hood is going to fall. So this is the entire length of the rope, and if we subtract off the Ly that we just found, we should be able to get the height. That is the change in height of Robin Hood as he swings. Okay, so you take the length of the rope and you minus off the Y component that you found using trig. Okay, you're now ready to do your first physics part. You're going to do Robin Hood's potential energy gravity before he starts to swing and set it equal to the kinetic energy right before he grabs the money bag. So you have height, gravity, mass, 1/2 mass velocity squared. You're going to use the height that you just found. You're going to use your planet's acceleration due to gravity, and for mine it's 9.9. You're doing the mass of just Robin Hood because he has not yet grabbed the money basket. You're going to use the mass of Robin again, and you're going to solve for this velocity. So that is what you do not know. At that point, Robin is about to have a collision with the money bag. So the second thing we're going to do is a momentum conservation problem. So we use the mass of Robin before the collision, the velocity that we just found from part 1. Okay, so we know that, even though I'm putting a question mark there, it's the same answer that we just got. Mass 2 is the money bag, and the velocity here is 0, so you could ignore this entire term. Before the collision, the money bag has no momentum because it's not moving. Then you would do Robin's mass times the final velocity plus the money bag mass times the final velocity. All right, so you get Robin's momentum before. So that's the momentum of Robin. Get it by doing his mass times velocity. And then at the end, since they're both the same velocity, you do the mass of Robin plus the mass of the money and solve for the final velocity. This is what you're solving for in part 2. That is the velocity of Robin and the money bag after the collision. It should come out less than the velocity of Robin before the collision. The money bag is going to take away some of his momentum. The final part of this problem is the projectile. Once Robin and the money bag become airborne, and for that we're going to use my horizontal vertical method. Horizontally, we have delta x, which is what we're trying to find. The velocity is going to be this velocity right here, the velocity after the collision. In the y direction, we're going to use how high we are above the water. Make sure you put it negative because we're going down. We initially have no vertical speed. Robin is moving perfectly horizontally when he reaches the money bag. Final speed is the speed he hits the water. We don't need to worry about that, so ignore that. The acceleration will be whatever your planet's gravitational field is, and time is what you're going to have to find. So you do one of your kinematics equations. You're going to solve it for time. Whatever you get for time, you're going to plug in here. Then you're going to use velocity equals delta x over t for the horizontal side. Again, you're using the final velocity after the collision. The delta x is what you don't know, and the time you're getting from the vertical. It's whatever you got down here. Once you get that delta x, realize that is only the delta x for once he lets go. You want to add that to how far the Lx is. That is how far he moved horizontally while he was a pendulum. Together, those will give you your total horizontal distance. So the program is going to ask you for 3 different numbers. It's going to ask you for the velocity before he grabs the money bag. You get that from part 1. The velocity after he grabs the money bag. That's from part 2. And the total horizontal distance, which would be the delta x of your projectile plus the Lx for the pendulum. I hope this helps. If you mess it up the first time, watch the video again and work through it carefully.